experiment. Why do we do diffusion experiment? Usually the main purpose is to find out the diffusion coefficient and how they vary with the factors that are affecting them. Okay, for self-diffusion coefficient, as I was mentioning before, it is something called tracer method. Through tracer method we do. What we do is, on a particular plane surface, we put a thin layer of radioactive isotope, and usually the bulk material is a single crystal of that metal or homogeneous alloy. To avoid the grain boundaries, either use single crystal or use very large grain, so that grain boundary contribution per unit volume is very less, negligible. You annihilate after putting a thin layer of radioactive isotope, which are called tracer. You annihilate for a specified time at a particular temperature. Then you section through at different distances. You section through and count the number of isotopes at that section at a particular distance x from that interface. So you get the composition concentration profile of the tracer, from which actually for this boundary condition, for this case, the solution of the equation is Cxt for the case which I just described. A sample on a particular surface, you are putting radioactive isotope and you are annealing it for a certain time. Cxt is given by some constant exponential minus x square over 4 dt. So Cxt is the concentration at a distance x from the original surface where you put the radioactive isotope after annealing for fixed time t. So if you, and what is m? M is the number of isotopes per unit area that you have put. So it is related to that. Number of isotopes per unit area that you have initially put on the surface. So a graph of ln c versus x square will be linear, whose slope, because you are, for a specimen, your annealing time is fixed. So you will get d. So from the slope you can get self-diffusion coefficient. So this is for self-diffusion or tracer diffusion coefficient. This is what you use. So for tracer or self-diffusion coefficient, we are not giving any subscript or anything, subscript, superscript. So simple. So that is tracer or self-diffusion coefficient. Now, so this solution is for self-diffusion case, where on a particular surface you are putting radioactive isotope annealing for a particular time. So C is from that surface at an x distance, what is the concentration after some annealing time t. That is given by number of atoms per unit area that you, number of isotopes that per unit area that you have put, multiplied by exponential minus x square over 4 dt. After annealing, you count C versus x, the C profile you have. From that, if you plot ln C versus x square, from the slope you will get the self-diffusion coefficient. That is what the tracer or self-diffusion coefficient, that's how it is obtained. For chemical diffusion coefficient, what is done is usually you butt weld two metals or two alloys like this, whatever I have shown here. So this is your original interface. This is along this interface. So two sides, two different alloys or two different metals, you are butt welding and annealing it for a specified time, after which you measure the composition profile say concentration of a particular element is varying from this side 0 to this side C0. So this is your concentration profile of that element.
So we take means two individual elemental crystals. We take individual elemental crystals.
You can take that. You can take two different alloys also, homogeneous alloy also, where a particular element's concentration may be in one side some C2, another side may be C1. Here in this case C1 is 0, C2 is 0. Now when you after annealing for a certain time, usually what you will find, the composition profile that you are getting, this is your yellow line is the composition profile, is not symmetrical along that original interface. Usually that is the case, and this happens because the interpenetration of the individual component element which are there, they are diffusing at a different rate. So one atom is coming from this side to this side, another atom going from this side to that side. An atom which the side which is rich in particular element which is of lower melting point, that will diffuse faster compared to the other. So that will go in the other side at a faster rate compared to the other element going in the opposite side. So there will be vacancy generated because there will be net loss of atoms in one side. So vacancies will be generated. Now we will find out how chemical diffusion coefficient B we have to find out experimentally B. There is a method called Matano-Boltzmann method. We just have seen how to find out self-diffusion coefficient experimentally. That is very direct. From that equation, LNC versus x square, you plot linear graph, the slope of which will give you self-diffusion coefficient. Now we are going to find out how to find out chemical diffusion coefficient from experiment. And our experiment is that type of experiment. So we have to somehow solve the equation, this equation, and an approximate method which was derived first by Boltzmann and first applied by Matano for this type of problem, I will be describing now. That's a graphical method. Okay, graphical method of finding this diffusion coefficient, chemical diffusion coefficient, and that method is called Matano-Boltzmann method. What is done here is your independent variables are x and t, time and distance. So you replace those two independent variables by some another variable called lambda. So this was first derived by Boltzmann and used by applied by Matano. That's why called Matano-Boltzmann method, where the derivation was like this. It was first x and t were replaced by a variable called lambda by x over root t, and if you replace substitute in this equation, can you do it on your notebook? Substitute and you do it. What I am saying that x and t, in place of x and t variable, you use lambda variable. To get rid of t. You will find out that why they have done so. to ultimate aim is to find out this from this type of experiment. That is the aim. So I am telling you the steps they followed. So what they did is replaced x and t, those are the independent variable, by one variable called x over root t, which is called, denoted by lambda. So you replace t from here using lambda and x. To do it on your notebook and tell me the expression. Are you getting this? Guys, you should do it very quickly. The other things you are just listening from me, your sharpness counts how quickly you can do these things on your notebook when I said you to do, ask you to do. You quickly do it and say that yes, it is. Because you do not need to have any prior knowledge, even if it is your first class, you can do this thing from first equation to second equation within a second. Okay. So make your mind alert. Is it okay? Is it what you are getting? Anyone? Yes. And from this equation, you just rearrange the things to take d in one side should be equal to minus half d is a function of a particular composition. So chemical diffusion coefficient at the concentration C means at a particular distance at the concentration C. So for this C value there will be a chemical potential difference, chemical diffusion coefficient value. You do it on your notebook on your own. Do not just keep copying. Which one? This one is got it. Just rearrange it to get to the next equation. Rearrange and bring yourself rather than copying. From this you just take D in one side.
There is one assumption, sir. T is not a function of lambda.
Yes, sir.
We have to do two substitutions.
Yes.
Then only we will get. Means first we have to take D as constant, then we have to take X as constant, then we have to substitute. Then we will be getting.
Yes, D is a function of C. You
no.
have done your experiment for a specific time. So your T is constant. So D tilde is function of C or X. That's what I am writing. D tilde is function of C, which is a function of X. Now, as your time for so you have done the experiment, you have annulled it for a specific time, your T is fixed. So lambda variable here, you can replace it with just X. Do it. Just if you write it in terms of X, wherever lambda is there, I am just writing X. Now, del X del C, it also corresponds to a particular value of C.
Sir,
This should be del X.
sir, we repeat this part.
Which one?
Why we are replacing lambda by x?
Because your experiment is done such a way that you have annealed the welded joint of that for a specific time, your T is fixed. That T is constant for a particular sample, for a particular experiment. That's why we are replacing lambda by X. We are getting this. So, chemical diffusion coefficient, which is a function of concentration, is equal to two terms. One is this term multiplied by this term multiplied by minus half.
Sir, T term will also come. Like DC will be minus 1 by 2T, then Dx DC at a particular C.
Do it means you have any confusion in this?
Minus 1 by
Yes?
2t.
Minus 1 by 2T.
Here you want a T, no? So, sorry, that was a mistake of mine. There should be a T. Thank you, sir.
No, sir, you will only
For lambda case, you do not have T, but when you are replacing lambda with x over root T, then you will have a T. So when I had lambda, that time there was no T, but when I am replacing lambda by x over root T, where T is constant for that experiment, then this T will come. That's what Saurabh said. Okay. So for a particular experiment, T you know. Now graphically, can you find out these two? Ritvik, you understood? For a particular experiment, our aim was to find out this one at a particular concentration. So graphically, let us see whether we can find out these terms.
Yes.
This is T is known that for a specific time you have any.
Area under the curve.
So del X del C at a particular C. So at a particular C value, del X del C is nothing but your X is this one. So del X del C is the slope of this. So slope will give you del X del C. At that C value, So what about C to C naught, X DC?
Area under the curve.
Which area? Which area?
C not by C. This upper side. This.
Your x curve is this one. Say your x equal to 0 is this one. But before that, let me to find out x dc, to find out this type of, say, any y x. So integral y dx from x1 to x2 is the area under the curve. Yes? Now area till you have to know that y equal to 0, where is y equal to 0? That you need to know, because till what area you have to take. That y0 you need to know. Here also, here y is x. Huh? So x equal to 0 you need to know. Your x curve is this area under this till what? Till this point, or till this point, or till this point. So x equal to 0 you need to know. That's why I wrote there that you need to first define x equal to 0 to be able to find out d. X equal to 0 is usually defined as which is the origin. Origin is that plane across which the net flow is 0. The net atomic flow, because two atoms are moving at a different rate in both sides. Net atomic flow is 0. So that plane across which net atomic flow is 0 is your x equal to 0, which is given by the area, the shaded area. This side, so across which plane the shaded area can be equal. This area and that area will be equal. So that particular, because your across your original interface, this is not symmetrical. So this area was less than this area. But across some other interface, these areas are equal. So that interface or that plane, across that plane, the net flow of atoms is 0. That's what we are defining as x equal to 0 or origin. Okay. So this plane. So this plane mathematically you can say x dc equal to 0. From 0 to c0, x dc